Okay, so let's look back at our example that we started previously for that RL circuit. And we're going to do a Bode plot for that RL circuit. Okay, and I'm going to choose particular values now. R is 1,257 ohms, and L is 0.2 henries. I chose those particular values because I get a really nice value for, well, not omega p, but we'll see the corresponding frequency in hertz. So R over L becomes 6,283 radians per second. And then FP is equal to this divided by 2 pi, which is 1,000 hertz. And then so my magnitude response in dB if you recall was minus 20 log of 1 plus. Now if I express it in terms of F instead of omega p or omega, you know, the 2 pi's in both the numerator, I had omega over omega p before, now I have F over FP. The 2 pi's just cancel out in both terms. Now, previously, you know, when I was looking at this, we had a plus term here, but because this term is actually in the denominator, I'll have a minus. So previously, I drew this Bode plot, you know, out to FP, which would be 1,000 here, and it went up. The only difference now is it would actually go down at a 20 dB per decade rate for frequencies above FP, and it's going to look like this. And it's going to decrease at a minus 20 dB per decade rate because of this negative sign. So let me actually switch over to some semilog paper here, where on the website you can print out this. I've got there's a link to a PDF, and on that PDF sheet there are actually 4 graphs like this on a single sheet of paper. So you can make 4 different Bode plots for 4 different problems. Now on that graph paper, it's got, you know, a little set of axes laid out like this to show you, and that should be in the lower left hand corner, because this is just laid out logarithmically along the x-axis here. It's laid out linearly along the y-axis. Now for our problem, you know, it had this interesting frequency here of 1,000. So these bold lines here are actually factors should be factors of 10. So our interesting frequency is 1,000 in this case. So I'm going to put it right in the middle somewhere. This would be 10, this would 100, then 10, and then above that would be 10,000, and then 100,000. And then I'm going to lay out, you know, I know this actually goes down, so I'm going to lay out like 0 here, and then I'm going to call this minus 10. In some plots you might call it minus 20, minus 40, but I'm going to lay it out like this, minus 20, minus 40, so this would be minus 30. These are my gains in dB, so this would be the magnitude response in dB here. Okay. And then now for my plot, let me actually switch colors here. Where'd my cursor go? There it is. See if I can choose red. I think that it's and let me actually switch over to the line tool. So the way I would draw this is, you know, I can draw the straight line here. My critical frequency was 1,000. So for frequencies below 1,000, I'm going to actually, you know, have my 0 equal my 0 dB line, a line equal to 0 dB for all frequencies f less than 1,000. So this axis here is actually, whoops, let me go back to my pencil. This axis is actually I didn't grab the pencil, sorry. Try it one more time. This axis is F in hertz. Okay, now let me go back to my line tool. Now for frequencies above 1,000, I start here and I'm going to go down at this 20 dB per decade rate. So at a factor of 10 in frequency above, notice I'm going to cross through this minus 20 dB point. And for a decade above that, I'm going to cross through this minus 40 dB point. And this line would continue forever. Okay, like, whoops, I missed it a little. There we go. So I think that, so this is what the frequency response of this low pass filter looks like on this Similog paper. It looks a little different than the plots we've looked at before. And we'll take a look at this in just a second in an LT Spice. When I've drawn these magnitude response before, I've drawn them on a linear scale in both frequency and in magnitude. But now I'm showing this in dB, and I'm using Similog X paper. By the way, on the Similog X paper, this is a factor of 10 here. This next solid line here above 10, this is actually, let me go back to my pencil. This would actually be 20. So this would be 12, 14, 16, 18, 20. This next solid line would be 30. This next one would be 40. Now as I get closer to 100 here, my lines actually get closer together. The next solid line is 50, then 60, 70, 80. Between 80 and 90, there is no dash line. Between 90 and 100, there is no dash line because they just get too close together. Between 40 and 50, the dash line would actually be 45. Between 30 and 40, I've got 4 dash lines, and that'd be 32, 34, so on and so forth. And so if you look at this point up here, this next solid line above 10,000 now on this Similog paper is actually 20,000. This would be 30,000. This last solid line here would be 90,000 on this paper. So that's how you find those points. So one more video to go in this lecture, and I'll return with that in just a few seconds.